Hello, welcome to another OSU Cyberlab video. To save time and afford diverse presentation perceptions, the voice was generated using text-to-speech in ClickChamp. Our lab uses a widely used open-source firewall routing software called pfSense. Many homes today have a router. They are special-purpose devices that can fulfill several network functions. They may terminate an optical fiber or cable. They route to and from the internet service provider. They act as a switch to connect devices. They probably even have radios for Wi-Fi. Larger organizations will likely have several dedicated devices to handle those functions, but many thousands of small businesses and organizations use regular PCs running pfSense software to manage their networks. To support multiple network segments, they install 2 or more network cards in the device. Then, like a Swiss Army knife, the pfSense computer performs a number of functions. You can run the install software from pfSense.org. It partitions the hard drive, installs the operating system, installs the pfSense application, and lets you configure network parameters. In our lab environment, pfSense coordinates 5 network segments acting as router, firewall, DNS forwarder, network address translator, NAT, and dynamic host configuration protocol, DHCP server. Our machines are virtual machines running in Hyper-V. That lets us deploy multiple machines in a self-contained sandbox to support learning. To protect devices in our network, we allow or block messages based on source, port, protocol, and/or destination. Some rules block messages. They just flat drop them. This is efficient, requiring little processing power. Other rules reject messages. Reject rules also send back a response. This allows the receiver to realize that a firewall disallowed communication. Sometimes it's better to hear no than to be ghosted. The other computer can immediately stop listening for a response that will never come. It's more efficient to hear back and check out than to wait for a timeout period to expire. But sending back a reply provides information. We may not want to give a potential attacker clues about our infrastructure by replying to a rejected packet. And, in some cases, these rejections can multiply into a storm of traffic where a rejection is replied to with another rejection. And we can create rules that allow the firewall to pass certain messages along. Got it? 3 rule types: block, reject, allow. This diagram shows our architecture from the pfSense perspective. Firewall rules can specify source, destination, port, and protocol. For most purposes, though, the source does not matter in pfSense. We will only use source in rules that are designed to allow certain devices to initiate certain kinds of conversations. Those are usually exceptions to a more general rule. Source would also matter in multi-layer router networks or in special rules called floating rules, but that is outside of the scope of our lab exercise. Let's try to understand why we will use rules that apply to all the sources. The key idea here is that messages are filtered before they enter the router, not as they enter a new segment. Messages from devices connected on the SecureNet segment are filtered as they come into the router using the rules for the SecureNet interface. If the message makes it past the rules for that segment, they will be delivered onto whichever outbound segment they target without any additional rules being applied. This can be surprising. This means that the rules on the SecureNet tab in the pfSense firewall rule interface do not protect the devices on the SecureNet segment. They protect devices on other segments and prevent unwanted communications that might leak out of SecureNet. Messages between devices on the SecureNet segment are handled by the switch, so the firewall can't block them. The rules on the SecureNet segment do not apply to messages traveling to a device on SecureNet from other segments. Do you see how this works? The SecureNet rules protect devices on other segments from inbound messages arriving from devices on the SecureNet interface. We would protect devices on SecureNet by blocking messages as they enter the router on other segments. Phew. That's a bit confusing. Importantly, rules are processed in order. Consider the 4 rules listed on the slide. They are assigned to the DMZ segment where a web server is connected using IP address 10.0.2.102. The web server uses a database on a different segment, SecureNet. Its address there is 10.0.3.103. The web server needs to make TCP connections to the database using port 3306 to get the job done. First, we allow the specific traffic needed to support the website's use of the database. That's the rule with specific IP addresses. Then we block any messages targeting private addresses. Since all our networks use private addresses, this blocks direct messages between devices on different segments of our network. But it does not block messaging to addresses on the Internet. As a starting point, possibly a risky starting point, we allow all IPv4 messages coming from the segment to move into the router. Then by default, pfSense blocks all messages from devices on the segment. Packets are matched against the first rule. If the packet meets the criteria, the response is applied and the firewall moves on the next message. But if it does not fit for this rule, the firewall tries the next rule. So, if the web server poses a query to the database, the packet enters the firewall with a source of 10.0.2.102, a target of 10.0.3.103, using protocol TCP and port 3306. That matches the first rule. The packet is passed along and the firewall moves on to some other task. But if we applied the rules in the opposite order, nothing would ever get past the default block all rule. For most cases, a set of specific allow rules are followed by some more general block rules. But actually, even small rule sets with only a dozen rules can become complicated as various exceptions are applied. And rule sets with hundreds of rules are not uncommon. As a side note, pfSense starts with rules at the top of the list. Other firewalls may start at the end of the list. But the effect is the same. Network engineers code the firewall rules in a particular and appropriate order. Then the firewall looks at each rule in order till it finds a match. We hope our web server never gets compromised. But it happens. It could well be that a zero-day flaw in a program included as a module in an application we installed has been discovered. You can read up on the log4j vulnerability to see what I mean. We hope we will notice right away, but even if we are fast, it will take a bit of time. Our firewall rules won't fix everything, but they can protect against a variety of subsequent attacks. Let's look at how the firewall would apply our rules. If the attacker tried to open the router configuration console at 10.0.2.1, it would fail. It would not be a match for Rule 1, so Rule 2 would be tried. It would match the second rule because 10. Addresses are private. Rule 2 is applied and the message is dropped. The attack fails. It's good to protect network management consoles. If the attacker tries to use a tool like Nmap to scan the OfficeNet segment, the scans would be blocked. Rule 1's target address is not on OfficeNet, so that rule would not apply. The request would match Rule 2 because 10. Addresses are private. Rule 2 is applied and the message is dropped. The attack fails. If the OfficeNet devices had been on the same network segment as the web server, there might have been trouble because there are likely a number of vulnerabilities on user desktops. If the attacker tries to open a shell to execute commands on the DB server, it would use port 22 for SSH. It would not be a match for Rule 1 because it is not on the designated port 3306. Rule 2 would be tried. It would match the rule because 10. Addresses are private. The attack fails. Because our web application is poorly configured, the PHP code lists the IP address of the DB server, the name of the database, and a valid password. If the attacker can read those pages, they have some valuable intel. Informed by this, the attacker tries the port for MySQL on TCP and the IP address of the DB server. This time, Rule 1 is a match and the message would be passed along. And, because a number of good practices for the application were ignored, the DB server could also be damaged. The lesson here is that network-level protections block some attacks and slow down other attacks. We have to protect our systems in multiple ways. No one protection is enough.